Hello, welcome to module number 3 of the lecture series for UT Dallas Summer 2018 Microscopy Workshop. In this module, like we discussed before, we'll be talking about detectors and practical aspects. There are three kinds of electronic detectors that are typically used on the microscopes. First one is a photomultiplier tube. It's a point detector. The second one is a EMCCD camera or electron multiplying charge coupled device camera, a field detector because it has got multiple pixels. And last one is a SCMOS camera or a scientific CMOS camera. It's also a field detector. In the coming slides, we'll be going in detail about each of them and understanding the working principles and how we can use them to the maximum extent. So if you talk about the photomultiplier tube or a PMT, it's a very simple device where the incoming light hits a photoelectric panel where due to photoelectron generation an electron is generated which is then multiplied over multiple stages. How does this multiplication happen? So imagine this to be a loaded apple tree which is bearing a lots and lots of apples, and now you throw one apple onto it, hundreds of apples fall down. You hope that but of course not always it will happen, but if your tree is good then it is going to happen. So in the same way here it's loaded with a lot of electrons because of a lot of voltage, and then secondary electron generation will happen, and each step it is going to be multiplied, or there's an exponential gain, and by the time it reaches the last diode it has already multiplied couple of hundreds and thousands of times, right? So that's how it works. Great thing is that it is ultra fast, has got a low noise and a high gain. Bad thing is that because it is only one point so there is no special information, and of course the efficiency also may be a question mark sometimes. So if you see here the spectral property, you can have all the way from UV to almost infrared, and but the quantum efficiency is not very high, and that's why these are great for bright samples, not for dim samples. But the gain that you can achieve using these kinds of detectors can be as high as like almost 10 power 8, which is like millions and billions which is like a very big number, right? uh, so these are mainly used because of their fast response. Say suppose you are trying to image one molecule in a very tiny volume, this is a great detector for that kind of a purpose, or for doing a entire field imaging really fast. Okay. Next is how do we use this in a daily basis on a microscope? How do we get a pretty image? That's the question. So this was the image that you were getting initially. For example, there are the parameters which you can control. Using this you can control the laser power. Of course there are a few other parameters which I will show you how they affect the image. So using this offset you can get rid of this background as you see here, right? And most of the background is gone, and then you can apply two kinds of gains. One is a preamp gain and one is a electron multiplying gain or HV. So both of their have their own qualities. Simple gain is going to multiply a factor whatever you see here, meaning whatever number is here it is going to multiply twice or thrice or whatever. So it is going to multiply both signal as well as noise in the same way. Hence overall signal to noise is not going to change, but the image might look brighter. On the other hand, HV is going to be a electron multiplying gain. How does that help? So if say suppose your signal is 10 and your background is 2, so right now signal to noise is 5. On the other hand, if you apply a twice gain, then your signal is going to become 100 and the noise is going to become 4 because it's square. So now the signal to noise is 25. So you can literally see that the signal to noise has squared, right? So that's why it is better most of the cases, but of course there will be cases when there are few bright spots and few dark, dim spots, and you want to visualize both. If you apply just this one, the EM gain, then you are going to suppress relatively the dim sample, right? So you want to use this one in parallel as well. So for most of the cases, like I said, this HV is good, but for some few cases when you want to image both dim and the bright, you have to use the normal preamp gain. Here is an example of how does the noise vary with PMT voltage. So this is my first PhD data on microscope, so I am really proud of it. So, and that's why I wanted to put up here. Just kidding. As you can see here, that the signal can grow really fast. It's an exponential gain within few hundreds of volts, and after some time it saturates to the maximum level. That's the 4096 bit because it's a 12-bit detector. We'll be talking about that in coming slide. But you can see that the noise is very small, and as the PMT voltage is increased, after 700 or 800 the noise becomes too high. So you always want to operate within like 700 or 800 volts, below that, not too low, not too high. Okay. Quite often I have seen a lot of people imaging in the pretty color mode, meaning green color or red color or blue color image. It looks great as a biology perspective because it's easy to differentiate between the three molecules that you are trying to visualizing, but it's bad because you can only see so much about the intensity. For example, if it is a saturated signal, you may not be able to capture that, and if it is saturated, then you are losing information here, right, which you don't want. You always would like to keep it in such a way that you have some bit of dynamic range so that you can actually accurately tell what is the signal there. And you also don't want to have background, so you have to set the offset in such a way that most of the pixels here are like a noisy background or like almost zero. Blue here means zero, red means it is saturated. So that can be achieved by clicking on this button called HighLow mode. So this is the HighLow image. High means high and low, and LOW, that is the low. Okay, so this can be and in order to adjust these parameters, like I have discussed before, you can adjust either the laser power or the HV to get to this final image. So what is a charge coupled device, or a CCD? So it's a very simple device, yet an elegant one, because the inventors got Nobel Prize for designing this device. So what happens is that there's a photoactive layer, light comes in, hits and generates electrons, which is stored temporarily here using a voltage. Next, what they do is that there is a change in voltage by pixel, and that way the electrons can be transported from one part of the chip to another, and that's how each pixel, once they record, they can transfer the electrons back to back into the measurement device, which can quantitatively tell how many electrons were generated, and that way you can quantify how the image was originally, because this electron generation is directly proportional to the amount of light that hit that pixel. So this analogy is a very beautiful analogy for how does the EMCCD work. Imagine these raindrops to be the photons which are collecting in these buckets. Each bucket is a pixel, and then once the collection is done, using a conveyor belt, it is poured into these buckets again, and one after another they are poured and measured in this measuring cylinder. This measuring cylinder can be 8-bit to 16-bit. Typically 8-bit means 2 to power 8 levels, so it will be 256 shades of gray, just like 50 shades of gray. 256 shades of gray. If it is a 16-bit image or 16-bit detector, then it will be 65,000 plus levels. So it's a lot of data. So most of the old detectors used to be 8-bit. Nowadays most of the detectors are 16-bit. So accordingly your image will be defined. If your CCD is collecting the raindrops like this, it is going to give you a good image, but it will be very low intensity because the amount of electrons that will be generated are 2, 3, 4 or a couple of hundreds maximum. If you want a great image, then you need to have a EM, electron multiplying, just like PMT. You have a serial register here which can actually amplify the signal in this form, so that even if at each stage the multiplication happens like 1% or 2%, but because there are so many stages, the multiplication can be really large, and that way the EMCCD is capable of detecting even a single photon. Sounds cool, right? Because of such a low signal to noise and such a high efficiency, it can measure even single photons, and that's why they are used in single molecule imaging. Why should we not saturate? I forgot to tell you, because that you have already lost the information, so it is not appropriate for quantification. And there are a few examples where I have seen that people have too bright sample, and man, your detector is crying, say that, oh, it's too bright, I cannot see anything, please help me. And that's when it shows these weird kind of structures. So it is happening either because your electron shifting from one pixel to another is not that fast, and that's why it is smearing up, so it has to be corrected. That is the clocking speed, or the sample is too bright, so you might have to either reduce the exposure or reduce the excitation, do something and help the detector stay alive. If you imagine this mode for long, then the detector is going to become blind. So I have seen a lot of, like, if you might have also seen, there are detectors which are like color camera, like the cell phone camera is a color camera. How does it work? So answer is simple. In front of the detection unit there is a filter like this, which can filter out colors in RGB format, red, green, blue. You must be curious, like, why are there twice the number of green compared to red and blue? It's because your eyes are more sensitive to blue and red compared to green, and that's why in order to compensate for that loss you have to have twice the green. And this is the close-up image of your screen. That's how RGB is looking on your screen, so that way you can actually see the colors. So it's a great way to visualize colors, but it's a wasteful way for a microscopist, because you are going to waste a lot of light and waste a lot of detector space. So it's always a good idea to use a monochromatic camera and with a filter in front of it, and you can switch the filters and then collect light. That way you are not wasting the precious fluorescence light. Nowadays the detectors like CCDs are going out of market. More and more CMOS cameras are coming into picture. Why? Because even though CCDs are great in terms of their efficiency, but they are a little slower and they're expensive. Newer CMOS cameras, like your cell phone camera and webcams, are really fast. You can see, like, when you are jumping and capturing that fast frames on the sea beach, you can actually capture those. How? Because they have made it parallel detection from each pixel, and that way you can get really fast images, like 400 to 2000 frames per second, which is really fast, right? So that's how it works. Good thing is that it is fast. Bad thing is that the noise will be higher, because here the source of noise was only here, or the serial detector. On the other hand, here each of these pixel is going to have its own noise, and hence all the noise is going to add up. So depending upon the application, you have to choose. If you are trying to detect like really teeny weeny signal in a lot of noise, then CCD is the way to go, or EMCCD. But if you have a lot of signal and you want speed, then CMOS is the way to go. And nowadays SCMOS, or scientific CMOS cameras, they have even lesser noises, so that way you can get really great images. So here's a comparison of the efficiencies of all the detectors that we discussed so far. these are the old PMTs, and nowadays in order to improve the efficiency we have GASP PMTs, gallium arsenide phosphate detectors. So these are different kinds of photoelectric materials. That way you can get better efficiency in the longer wavelength regime. Most of our microscopes have these and not these, so that way you can get a twice better signal to noise. Next is EMCCD. EMCCD can give you almost like 95% efficiency, like, which is amazing. But of course they come with a cost. Each PMT can cost you just like $1,000 or $2,000, but EMCCD can be as much as $32,000, $35,000 for just for 512 by 512, so which is really expensive, like 16 times. And CMOS camera, like they cost about $5,000 or so, and they are relatively very good efficiency nowadays, and they are catching up with the EMCCD. So very soon I believe that as the time progresses, EMCCD is going out of market, hopefully, and SCMOS will replace, because they can have a really large pixel area and fast. Like I had promised earlier, I was about to discuss about the optical resolution. How do we get it? So when the light passes through an optical element or a lens, it is going to form a diffraction pattern like this, like we had discussed in the first few slides. And the size of this one is going to be determined in the xy by this formula and in the xz by this formula. If you observe closely, it is only dependent upon the wavelength and the numerical aperture, and not on the magnification. So if you have two lenses like 60x and 100x, but if 60x has got a higher numerical aperture compared to 100x, then 60x is actually going to give you a better resolution. So be mindful of that. And now based upon these, let's see how we can resolve between the two objects. If the objects are really close by, you may not be able to see them as two different objects. Remember the example that I gave of the car that is really far away, and the two headlights are looking so close you cannot see them as two objects. It is this similar case. But as the car gets closer to closer, when the maxima of one is in overlapping with the minima of the other one, that is when we say it is resolved, because there is some bit of contrast change that you can see between these two peak points, right? And here it's very well resolved because they are really far away. So that's how you can say that, oh, my object is whether resolved or not. And here's an assignment. I would recommend that you should read it. That way you can get a better idea of what we are talking about. So now the question comes, everything is great, you can create these kinds of patterns using lenses. If you use a lower NA, you can get bigger pattern. If you use a higher NA, you can resolve between the smaller patterns. But how do we convert that into a digital image? So if you see, this is more like a frequency, right? Not just whenever we think about frequency, we only think about radio, FM and things like that, right? But if you see here, spatial frequency, these bright and dark spots can also be like a frequency, right? If these are really far away, then this is a low frequency, this is a high frequency area. So if we try to sample that, and if we draw a line profile here, we are going to get analog signal like this. And if you want to digitize that, we can either oversample, we can sample it so fast that we are getting all the information, but it is a wastage of your energy because you don't actually need so much of information. Correct sampling is good enough, but if you undersample, then you are going to lose information and you will not be able to reproduce this. The whole goal is to reproduce this using the acquired data. So how do we do that? So the ideal way is to sample at the rate of at least 2 times per cycle, meaning if there's a bright spot here and a bright spot here, in between the two, you should sample it twice at least. Why do we do that? So here's an example. Say suppose I had a signal like this and I sampled slowly and I got a bright spot and a dark spot. Now if I want to recreate using these, I can fit a sinusoidal function of this frequency, but I can also fit another sinusoidal function of this type, right? Which one is the correct? I don't know. You cannot tell. But of course, any sinusoidal wave with a frequency lower than this cannot fit through these two data points. And that way I am sure that the lowest frequency that passes through these two data points is this one, whatever I have shown. Anything shorter than that, shorter than anything of a lower frequency than this cannot pass through. If I wanted to actually sample this one, then I would have to have extra data points, and that way I would be able to do it. But still again, this will be valid only in this area, but if you are trying to image in this area, then you have to have even more data points. And if you don't do it correctly, then what happens is that you start getting these kinds of weird fringes, and this is called aliasing. I would recommend reading more about this in Nyquist sampling. You can Google and then find more about that. So it's always a good idea to make sure that you are on the right sampling rate so that you don't end up in getting images like these. So in our microscope, luckily we have a system where you can click optimize and the right optical resolution and pixel settings can be done. But of course you should be vigilant on doing it yourself so that you are sure that whatever you are doing is the right thing. Here is an example of what happens if you do the wrong thing. So if you have an object and if you didn't choose the right magnification or the right objective, you are going to end up in a blurred image. And even if you say suppose chose the right objective and chose the right pixel size, if you don't have enough pixels, then you are going to get a pixelated image. And here is a real life example of how this is going to affect your results. Say suppose if you have 3 objects, 2 of red color and 1 of green color, and you wanted to see whether they are co-localized or not. What you do is that you image using an objective. If you use the right objective, then you are going to get point spread function like this. If you used a wrong objective of a lower numerical aperture, then the point spread functions are going to overlap, right? And then you will say, oh, they are co-localizing. So that means you have to have the right objective. Then comes the sampling. So like we discussed, we are going to sample at least twice for a point spread function. And that way we will be able to successfully tell that the red and the green are not co-localized. On the other hand, if you, even though you chose the right microscope objective, but if you didn't sample it enough, you will be ending up in a false co-localization. So always make sure that you are choosing the right objective as well as the right sampling. And one more important point which I want to make here is that even if you are able to see co-localization in some cases, that doesn't mean that they are molecularly interacting, because your microscope can only resolve so much. This is the optical resolution it can achieve in this case. So if you want to prove there's a molecular interaction, then you have to show some biochemistry experiments. What is a Z-drift compensator, ZDC? So suppose if you want to image a sample for quite long, like hours and hours or days or weeks, then it is going to drift as a function of time, because the temperature in the room might change and the sample might drift. And this is how without the Z-drift compensation it is going out of focus, but with ZDC on you can actually prevent the sample from going out of focus. How does that work? So there's a laser, infrared laser, which goes in and reflects back from the cover slip and is detected here. Whenever there is a movement of this cover slip up and down, it is detected here, and then the microscope automatically moves the objective in such a way that it is always in focus. And last few things, if you are imaging it for days and hours, you might like to make sure that the temperature is right, because if you are imaging a bacteria, room temperature is fine. But if you are trying to see some kind of a live cell or mammalian cell, then definitely you might like to use an incubation chamber, so that you can have a CO2 supply and 37 degrees Celsius temperature, such that the cells stay alive. And if you are having a very large field of view that you want to image, but uh, there are too many cells here which you want to see, but it's very large sample like this, then what you can also do is image stitching, meaning like you acquire one area like this, one area like this, and then you can automate the entire microscope to acquire the entire field and then stitch it together for you. So this way you can get the entire field in one go. So with that, we come to the end of the presentation. If you have any questions, feel free to email me. And with that, over and out, and happy imaging.